So here we have an example of linear regression in action. So we're trying to use house size in square feet as our independent predictor, and we're trying to predict house price in thousands of dollars. And you can see that the lines that minimizes the square error loss is y equal 0.232x plus 246. If you plot the loss function against the parameter w0 and w1, you can see that the function is actually convex and it has a unique global optimum here, global minimum that we can reach, and this is actually that global minimum. So w1 is 0.232, so it's somewhere here, and w0 is 246. Now, if we use regularization with regression or classification, there are two types of regularization approaches. There's L1 regularization, which essentially adds a penalty that is proportional to the number of parameters in the models. And this type of regularization tends to force some parameters to be zero, to have zero weights. So it tries to get the model to converge to the smallest model possible by eliminating completely some parameters. If we use L2 regularization instead, which is what's on the right here, this one, it tries to minimize the square root of essentially w1 squared plus w2 squared. And that's why it's called L2, because it takes the L2 measure of the w vector. So in that case, you're not going to eliminate any parameter. You can see that you're still going to have a w1 and a w2 at the optimum vector, w star, versus the L1 regularization, which essentially ends up eliminating w1 completely and just keeping w2 in that case. So the type of regularization determines what type of weights you're going to end up with. And again, we're going to experiment with all these types of regularization or our code in this class. Now, what if I'm not interested in predicting a continuous value, but instead in classifying data points between two classes, binary classification? So in that case, I'm doing linear classification rather than linear regression. So all I need to do is essentially build a decision boundary, which in that case is just going to be a line or a surface, if I'm talking about higher dimension, that separates the two classes as best as possible. And so my hypothesis in that case is still going to be the equation of a line, but essentially I'm going to define a threshold and say, okay, if my prediction h of x is higher than a specific value, then I'm gonna say that this specific example x belongs to class 1. If, however, the h of x is below the threshold, then in that case, this example belongs to the other class 0. Okay, so that's the only difference here, is that we're gonna pick a threshold and use it to separate the two classes. So in that case, there's a possibility my loss function has to be changed a little bit, because I don't really care how far is my prediction h of x from a true value y, but I just want to make sure that if the true class is 1, that I actually predicted 1, and if the true class is 0, that I actually predicted 0. Okay, so it doesn't matter I was off by how much or how far from the threshold I was, as long as at the end of the day I made the right decision or the right classification, I will be happy. So that will require some modification to the loss function to account for that. So this is an example of a perfect classifier, for example, on the left here between x1 and x2. You can see that with a linear classifier, we're able to perfectly separate the two classes, the red and green classes. The classifier on the right, however, we can't separate the two classes with a linear classifier, because you can see that there are some green dots that on the top of the line, and there are some red dots that are below the line. So these will be the errors that we did in classification in that case when we use this decision boundary. Now, as the number of training updates increases, of course, I should converge to a higher proportion of correctly classified example, right? So if the data is separable, so if it's possible to build a decision boundary that separates the same data, I should be able to get this boundary. Again, this is all on the training data. The question remains, which is most important for us, is how well this model will do on unseen data. That's what we care about, really. How well does it generalize? Now, instead of using a threshold, a strict threshold based on h of x, and we don't like these sharp threshold greater than 0.5 or less than 0.5, and the reason why is what do we do if we're exactly at 0.5? There's no, is the program going to crash here? What kind of decision do we do if we're exactly at the boundary? So we prefer instead to use a smooth transition or a smooth threshold, and we use what's called the logistic function, which is essentially defined as the logistic of a variable z is equal to 1 over 1 plus e to the negative z. So if in our case here, we're applying this to w dot x, which is essentially the h of x. So it's going to be 1 over 1 plus e to the negative w dot x. Okay, so let's see what happens. So if we get a very large positive value here, so our classifier is confident that this point belongs to class 1. So we get a very large positive value. What's going to happen is e to the negative, let's say negative infinity, is going to be 0. And the output is going to be 1 over 1 plus 0, which is 1. Okay, so that's very good. Now, if we get if our classifier is very confident that it belongs to the other class, so we get a very large negative value. So in that case, it's going to be 1 over 1 plus e to the infinity. So it's going to be 1 over infinity, which is 0. So that's how the logistic function will give us the decision to which class a given training point belongs. Now, close to the boundary, we're not going to have problems, okay, because we don't have a sharp threshold. So you can see here on the left is if we use a strict threshold at 0. So if we say if it's positive, you're class 1. If it's negative, you're class 0. What happens if I'm at 0? We don't know. And then plus the second problem is if I start using this threshold in my loss function, I'm not going to be able to find a gradient just because I can't differentiate this function at 0, right? You can see that it's not a smooth function, so I can't find a derivative at 0. However, if I use a logistic function instead, which is in chart B here, this one I can find the derivative at 0, no problem. It's differentiable everywhere. So that's why we're going to replace the sharp threshold with a logistic function, the sigmoid function, and we're going to call this logistic regression as a result. And you can see here how it converges in that case if I use logistic regression on the previous data. Okay, so all the models we discussed so far were parametric models because we were trying to learn the parameter vector W using a set of training point big N that was given to us. Now there is another family of models which is called non-parametric model, and these are not defined by specific parameters. For example, piecewise linear function if you have a set of training points and you just connect them by a piecewise linear function, in that case, there's nothing to tune in that model, essentially, right? There's nothing to train because you're just connecting each two consecutive training points with a linear function, and that's going to be your model, essentially. Or the simplest type of model is a lookup table, right? So essentially, you have all your training example in a table, and when you get a new value, you check your table and you return that specific output. Okay. Now the question happens is that, okay, what if you get a new value that's not in the table? Okay, what do we do then? So in that case, you can start using non-parametric approaches, and the easiest one to use really is k nearest neighbors. So given a query for xq, so you're interested in finding the output for xq, but xq is not in your table. So what you're going to do is you're going to try to find values that are close as possible or near as possible to xq in the table, and then see what the output is for these values and take their average. Okay. So for example, if my k is 3, which means I'm going to be using 3 neighbors, and I have a new restaurant, and that new restaurant is nowhere in my table, I'm going to find the 3 nearest restaurants, and we still have to define what is nearest means. So I'm going to go look up the 3 nearest restaurants and look at the decision for these 3 restaurants. I find that one of them was a yes, the second was a no, and the last one was a yes. So I decide that, okay, so for that new restaurant, the decision then will be yes, just because that's a majority rule in that case. And typically we select that k nearest neighbor, k is usually odd, so we don't get ties. Okay. Now the only question that remains is, how do you define nearest? Okay, so there are multiple ways. The first way is using Euclidean distance, which is essentially the square root of the, the difference between the two vectors. So your first restaurant is defined with a vector x1, your second restaurant is x2, so you just find the L2 distance between x1 and x2. Or you can use the Manhattan distance, which is essentially you find the maximum value between x1 and x2. So you do absolute of x1 minus x2 and then take the biggest element of that absolute vector, and that gives you the L1 or Manhattan distance. There are other distances you can use as well, and there are many variations, but these are the two most popular ones. So in that case, k nearest neighbor would give us this boundary right there. So it's not the linear boundary, it's that shaded area. So essentially, as k increases, obviously if you just use k equal 1, so essentially you're using the one nearest neighbor. So in that case, you're overfitting because you're just finding the nearest point to the new restaurant and using that. What you want to do is you want to average. So if you use average over 5 neighbors, so k equal 5, you can see here that the decision boundary is much smoother, and there is only 2 restaurants that are misclassified between the yes and no in that case. So there's much less overfitting as the k increases. The problem is if k gets way too big, then in that case you end up with a bias problem where the model is just too simple to capture the differences between the two classes in that case. So it's a trade-off that requires tuning as well, like we discussed earlier with hyperparameter tuning. Okay, so let's stop here, and I'll see you in the next part of the lecture.